Bueno, pues muchas gracias a todos por acompañarnos en esta jornada que esperamos que sea de interés para todos los que estáis aquí. Quería presentar a Peter Staar. Peter Staar cursó sus estudios de grado en la Universidad Católica de Leuven y sus estudios de máster en el Instituto de Tecnología de Zúrich en el campo de la física teórica. Continuó su doctorado en física teórica en el mismo instituto de Zúrich y se centró en el estudio de superconductores a altas temperaturas. Terminó su doctorado en 2013 y empezó a trabajar en IBM Research. Actualmente es investigador en el Cognitive Computing and Industry Solutions Group y trabaja en el desarrollo de algoritmos cognitivos de nueva generación. Ha sido finalista 2 veces en el prestigioso premio Gordon Bell de la ACM, primero en 2013 por su artículo Taking a Quantum Leap in Time to Solution for Simulations of High TC Superconductors y después en 2015 por el artículo titulado At an Extreme Scale Implicit Solver for Complex PDEs, Highly Heterogeneous Flow in Earth Mantle. Nos va a hablar de Cognitive Computing and Materials Design y lo que va a hacer es describir una aplicación cognitiva utilizada para el descubrimiento de aleaciones de aluminio y luego va a mostrar cómo estas mismas técnicas de computación cognitiva se pueden transferir al campo de la biomedicina. Muchas gracias.
So the talk will be kind of cut up into 3 parts. First, I'll give you just kind of an introduction to cognitive computing. So we already had a little bit there. But I will go really deep down to the basics, what it is really about, okay? Because there is a lot of noise, there is a lot of garbage going around, which I don't really like so much. Then I will, once I've explained what it is and how we envision, implementing all of these technologies, then I'll guide you through one of the projects that we did with the client. And at the end, I will give you a demonstration that's basically the technology that we developed for this client, and I will also give you some other demos from other current projects that are going on. They're not perfect yet. I mean, they're in the process of being developed, but I think they will give you kind of a feeling as to how broad the cognitive computing. Good. So, cognitive computing. So, the first question you have to ask yourself is, what is cognitive computing? What is the difference between analytics, artificial intelligence, and cognitive computing, right? These things get always messed up in a terrible way, and I think it doesn't help us. Okay, we are not, IBM is not in the business, although we might play with that. I have a friend at the lab who is playing with, for example, robotics and, trying to interact with robots. But, IBM is about, transforming business enabled by technology, right? And what this cognitive computing basically does, it's built on top of all of the stuff we have. Okay. Well, can everybody hear me? Am I loud enough? Okay, I think Okay. Oh. Okay, so I'm used to shout, so right. Okay, so we are transforming business by enabling technology, and the idea of cognitive computing is essentially the following: it's automation of human processes. Okay, what does that mean? Human processes that are laborious, that nobody really wants to do, but everybody has to do. Okay, looking at images, medical data, for example, is very laborious. It's very time-consuming. It doesn't scale because we don't have trillions of people on this globe, and it's not something we want to do. We want to just look at the very special cases that are interesting. But if for most of the cases, we can just pass through them and directly identify things. Another case where I'm very much involved in is reading papers. We're all scientists here, or most of us are. We all need to read papers. But the fact of the matter is, today, every month, how many papers getting published? 10,000, 50,000. How much can you read? You cannot keep up. It's impossible to keep up. So you need a system that allows you to automatically read, automatically extract the data, and then being able to query that data in an intelligent fashion. Okay, if that's, at least in my perspective and what I'm working on, that's the core part what needs to be accomplished. Okay, and so that is essentially what cognitive computing is to me. Now there will be other people that have different views, and I'm all for it. But for me, that is basically the goal. Now that is what cognitive computing is. How are we going to establish this? Because it's nice to dream about what we want to do. The other thing is how we have to do it. Essentially, and this is a snapshot of any project that we do, essentially the cognitive process happens in 4 steps. It's basically a data pipeline. You start with, for example, a bunch of papers, a bunch of PDFs, and at the end you want to have a system that allows you to query the data or whatever is in these papers or documents. That is cut up into 4 steps. First, you need to gather the data. Gathering the data means reading the papers, getting the papers, essentially, getting the relevant databases. There are wonderful databases with structured data, perfect. All other kinds of things. This might even be social media, although I'm not heavily involved in that. But there are many, many, many different data sources. Here already there is a huge problem. Okay, so what used to be the typical way of doing things is doing with databases is structured data. Now it's pretty obvious that when you are trying to extract data from a technical paper, it is not going to be structured. Simply because typically what happens is you describe some process, and I will give you some examples, but you will not, in a paper, you will not find everything. You will find only a part of what is described, and most of it is basically either left up to the imagination or it's just not there. So you have a huge problem of gathering unstructured data, and dealing with unstructured data is a central part of cognitive computing, right? How do you store that? How do you query that? The second part is, once you have gathered the data, is you need to annotate it and you need to make sense of it. So that basically means, and this is the creative part, here you're going to say, I'm going to start making links between extracted data, and I'm going to represent this now in a knowledge graph. That is basically the definition of what a knowledge graph is. It's basically links that, based upon a hypothesis that you have, you say, for example, if I look at all the materials described in one paper, they will have something in common. So, for example, you will make links between all the materials described in one paper because a guy is talking, for example, about magnetism or superconductivity or God knows what. So that is a hypothesis you put in. So then all of the materials that are mentioned in this paper are getting linked. The third part, after you've made this knowledge graph, and this is based on some hypothesis, the third part is starting to build algorithms that then analyze this knowledge graph, right? And for this, there are very advanced things, very advanced theories and algorithms that allow you to analyze large graphs. That's what it's all about. A knowledge graph, at the end of the day, is a graph. A graph is a mathematical entity, and on this mathematical entity, you can do all kinds of operations. And that's what's called the reasoning. For example, you can do inference. You can do, okay, what is, for example, the most important node in the graph in a certain field? What is, not important? What is not looked at? What is looked at all the time? And so on and so forth. And that's the reasoning part. So my personal thing is in these these 3 things. And then the last part, which is still very important, but I'm not super involved in that, although maybe I will be in the next coming months with another project that's coming up, is how shall I say, the consumption of the data, right? This is typically, especially because I come from a theoretical physics background and you care about algorithms and data and high performance computing, but at the end of the day, if you write a question, you need to be able to write that in an intelligent way. You don't want to be writing, you don't want to spend half a day trying to come up with a query. And also, you want to be able to digest this data in an intelligent way. So you want to have a visual representation or a good answer that allows you to make sense out of this. And part of that comes back to then also giving you evidence for why the system answers the way it does. Okay, so I've been talking a lot about this slide because that slide I want you to keep in your mind. That is what it's all about here. Where does this all come from, this cognitive computing? Basically, it started with this text analytics, right? Natural language processing. If you, for example, want to read a paper, you better know how a language is understood by humans. And that's what it started with IBM Watson, essentially, in the early days with Jeopardy. Right? They did basically natural language processing, which basically is some kind of text analytics, and then they connected this text analytics with some knowledge graph, a very rudimentary one, but if it's good, if it's rudimentary but it works, it's perfect. So that's where it all started from. The second thing on which the cognitive is built is a machine learning approach that allows you to not have to code everything anymore. Now, this machine learning can be typically split up into two parts. There is the traditional one, which is based on rule-based approach, which typically works, let's say, in 80% of the cases, or maybe 60%, depends a bit on the field, right? So the rule-based approach is good because it's very fast. It allows you to get very quickly some rudimentary data. However, it's not very accurate. There will be a lot of loss, and that's why then the machine learning, the deep learning comes in, which is a bit more fuzzy. So there is, you need to know what you're doing, but typically once you then, on top of the rule-based approach, you put a deep learning machine, you can then get much more data out at a much higher accuracy. So this is part of, the how we do things. I want you to look at this sentence. So this was for our in our metallurgy case study. So we were handed not papers, but patents, and patents are even worse than papers because they're, scientific subjects written by lawyers. So it's absolutely horrendous. Now, for example, let's identify just one sentence out of a patent that is maybe 20 pages long, how much data is in there, right? So this ingot, or that ingot, an ingot is basically a block of aluminium, was scalped, homogenized at 800 to 900 degrees for 24 hours and hot rolled to a 6-inch thick plate, So essentially what you want to do, and I think you can directly make the link to any type of biomedical paper, there will be also these very, very technical sentences in. Essentially what you want to do is you want to make an entity. They say, okay, so now we know that there is a data point here. It's a block of aluminium. It was processed in some way at some temperature, and then, it was put in a certain format, right? And then later in the text, they will say, and that ingot had following properties and, was good or was bad. So essentially what you want to do is when you're reading this paper, you want to start extracting these data snippets, right? And the whole point, what the cognitive allows you to do is to do exactly that. Gather all of these data snippets, which become a huge, huge, huge unstructured database, essentially, and then do statistics, do advanced algorithms on top of that. Can you now do predictions of this? So given all of the stuff you've extracted, can you now do a prediction over a certain strength? And I will give you a demo. So and this is the thing what basically happens with the machine learning. So for example, you have the ground truth. So the machine learning works as follows. You need to have a ground truth. The machine starts to learn from this. And then once it learns, it tries to redo the same document or a few documents that you have intentionally left out. And then you see how well you're doing, right? So for example, the ground truth here was annotated by hand by some people. You see on the top essentially what they did, and it's the same as the previous slide with the sentence, and on the bottom you see what the machine basically got out. Okay, so that was. So I want to go actually a bit further into detail. So for example, this is now a geology project in the oil and gas industry. And there, it's even messier. Okay, metallurgy is still quite nice. Geology is a really, really messy science because a lot of people have hypotheses and theories, and you need to be able to slash through them. So some people will say this, the other people will say that, and they will start fighting with each other, and so on and so forth. And so what you need is a system that allows you to read through these geology papers, say, okay, this school of people thinks this, that school of people think that. Do we find evidence for it? Is it maybe a dream? Could be. People make up stuff. So that's what we're doing right now. And so, for example, this is a typical paper, and then you see here some expert geologist has been annotating this. This is the way they do it now. Of course, that expert geologist is a very expensive one. He can only do maybe 1 paper a day. He will make mistakes. He will put his own, in his own way, that he will extract what he thinks is important, but maybe some other person thinks something else is important. So it's really flawed. And at the end of the day, what they want to do, for example, is they want to say, look at this complicated, this is an idea I have in my mind, yeah? This is the idea, for example, for a basin, okay, or for a play, how you find oil, whatever, doesn't matter. Can we now fill in the gaps that the paper tells us this, you know? What is the paper telling us about this stuff? That is what cognitive is about, right? Fill in how the paper is describing this concept. And maybe this concept is wrong. Maybe I want to change something because we want to find different concepts. Can we rerun the system again? If you need people to go over it again, it's not possible. But with a machine, you can do this stuff. So this is the way, for example, they write the thing down with Excel files, okay? And you can see this is not just papers. We are now also ingesting posters because a lot of data gets published on posters, magazine articles, I mean, you name it, okay? And now we just parse all of this data. We try to extract the relevant data, but now objectively by a machine, and see what we get out. And then afterwards, we will do statistics on that. This is, for example, the stuff I'm working on together with a student. And again, for the students under you, we are always looking at the best and the brightest. So if you think you got it, if you think you're good enough, you can do an internship or even a PhD. I don't have a Spanish person as a PhD student yet, so that'll be good. Okay, so opportunity, exactly. I will try to collect every country in Europe now. Okay, so this is, for example, one. So again, you see a geology paper. We split up the text and the graphics. Then we do rule and deep learning parsing. We annotate, and of course now, part of the stuff is also to see what are the graphics about. You know, what maps are they showing? You know, can we, whatever. You know, what are they doing in there? And then relating all the numerical data that's in the map back to the text, right? So that you can start querying this. This is another thing that we did. This is for a material science project. Material science is much closer to my heart. That's my former love. Okay, so. We do this because we really, really like to. This is another student. We do this. So again, so you have these complicated graphics. You have you see that, for example, we have the text here that we extract. We have the figure captions. So now you could say, I want to do a query over not the text. I don't care about the text. I only care about figures. So query me over all figure captions, okay? Is there a figure that describes this material and that property? Well, I don't know. But ask the figure captions. And maybe there is one, and then you find already what you're looking for, right? Okay. So this is at this point, it's just parsing. Then, of course, you need to annotate, right? You need to say, okay, so now I've extracted all of this text. I've extracted all of the figure captions. I've extracted blah, 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 blah. Now I want to annotate. This is, for example, a material. This is a property of a material. This is an author. This is a reference to a paper according to, all of these kind of things. So that's what we then call at IBM, I don't know whether this is international, like deep parsing. Okay, that's what it's all about. And this, again, needs to go very quick. So we have parsing, and then we have the deep annotation or the deep parsing. Okay, so this is maybe a... Let me now go to the second thing. So this was the first part. So I think you can always ask questions. I mean, I promise not to bite. So what I will do now is I will go a deep dive into a particular case study that we did for the material science, okay? And this was metallurgy. So this was a company that, I think they invent around 40 patents, 40 new aluminum alloys a year. They are feeling the heat because there are other companies that are also at this level, so they want to innovate more. They want to, and if you want to innovate more, you need to be able to get more patents out, and so on and so forth. And so this was the deal. So can we find new aluminum alloys with a certain prescribed set of properties? Okay. And so when you start with these kind of projects, we can go back to the data pipeline and explain that, but that's at the end of the day, nobody's interested in that. At least from the client side. From our side, yes, of course. But from the client side, what they want is a solution. They want something that works, okay? The rest, nobody cares about. So for example, what we did is we said, okay, let's first start with a bunch of questions you would like to ask. So imagine that you get all the extracted data. What are the typical questions you would like to do? And there are essentially two types of questions you can do here. There is the statistical questions that allow you to query what have you extracted? What data is out there in the literature, right? What are people doing? These are, for example, the first three questions. You know, I give a bunch of properties. Has anybody already found something like this? If so, I don't need to invent anymore. I have it, right? What is a typical range for a certain property given a set of constraints? So if I put in, I don't know, lithium into an aluminium alloy, you know, what is its property typically? You know, is it going to go increase? Is the range big? Is it small? And so on and so forth. The second part, and this is where HPC comes together with big data, is about prediction, okay? Now you have all of the data available, right? And there are trends in that data. Now you want to say, well, maybe we don't have, you know, an aluminium alloy that satisfies these properties, right? But we want to make one. So how do you make it, right? You basically, now you have your constraints. You say, these are the properties. These are, you know, I want to have an elongation of so much. I want to have a strength of so much. It cannot have, for example, more than 2% of silver because silver is very expensive and definitely no gold, right? Can we do it? Are there trends in the data that tell me that you can do it or not, right? And if so, if there are trends, can you tell me what I have to put in? Very simple, right? So these are, well, the question is very simple. The implementation is a bit different. Now, to do that, you need HPC, okay? You need high-performance computing because these type of predictive algorithms require that you touch a large section of the data, right? If you typically do all of these, Hadoop and Spark and stuff, what you do is you typically don't touch big parts of the data. You look locally at your data. So then if you have a local data algorithm, it's fine. But if you really want to do predictive stuff, you need to touch big chunks of the graph, and then it becomes a heck of a lot more difficult, especially if you want to do this on the push of the button, which we want to do. Okay, so let me go directly to here. So I talked about concept of a knowledge graph, right? So how do we start in a very specific case? What do people do typically? They put, as I showed you before, they just take a paper, they fill in they make a big table, and then they say, well, let's fill in the blanks, okay? Now, what you see, the gray stuff is all the things we don't know, right? Now, if you store it like this, it's very, very stupid because all of this, you know, all of the things you don't know, you're still putting your required space. So if you're in a natural database, this would be a no-go. That's why we go essentially to a knowledge graph, and in a knowledge graph, essentially what we do is we take, for example, every row here is an aluminium alloy. We make a node out of this, right? And we make also a node out of every column because that's a property. And now you just simply say, okay, let's make a link whenever there is, you know, a non-zero value, for example, between a node and between a row and a column, right? And so essentially what happens is a knowledge graph is actually a very natural extension to very sparse databases. And the way the mathematics behind it, why is this? Is because if you look at the graph from a mathematical point of view, a graph is nothing else as a sparse matrix, okay? And this table is a matrix, and it's a sparse matrix. Sparse matrix means you have a matrix with many, many zeros in them that you don't want to store. So that's the knowledge graph is essentially natural from a mathematics point of view, is a natural tool to describe the sparse data. Okay, so this, again, I want to keep you this in mind. So if you have this data pipeline in mind, we had this knowledge graph and the concepts and all of this. This is where this gets split up. So you have two things. You have, on the one hand, the creation of the knowledge graph, in which you take the data, and then you make hypotheses, and these hypotheses leads to links between the nodes in your graph. And for example, one way to do that is to say, if the doping elements are just slightly different from one material to another material, I could imagine that the properties are the same because it's a continuous thing, right? Not always, but it sometimes is, or most of the time is. So you can now put in hypotheses. You change a bit the doping, you change a bit of silicon. I don't expect, for example, that the tensile yield strength will change a lot, right? These are hypotheses. And then once you do that, you create a knowledge graph with these hypotheses, then you unleash algorithms on them to then start making, to analyze, okay, so what is, for example, given all the aluminium alloys with silicon, what is the most important one? What is the most used? What is the best one given the fact that I want to have the strongest one, and so on and so forth. And of course, the algorithms also correlate to predictive analysis, which I will show in a minute. So this is, for example, a knowledge graph. So another thing I want to actually stress is that in a knowledge graph, you can put anything as a node. That's actually very, very nice. So you think of something, it can be a node. It can be an author. For example, for the knowledge graph of these materials, we have alloys. So these alloys they come out of a big book with 501 aluminium alloys. These are the ones that come from the literature. Then you have processes. How do you make aluminium alloys? How do you, for example, make them stronger, make them better, and so on and so forth. Then you have, for example, product nodes. So these are things that typically small little snippets of text that describe how an aluminium alloy was made in a specific instance, and so on and so forth, for which you don't have most of the data. Typically, this is very sparse. You have property nodes and so on. And each of these category of nodes now, they start to link together. And now once you have all of these links, you can first of all traverse the graph, but you can also do then all kinds of cool algorithms. So just to give you an idea, so these are all the nodes that we had in the graph about properties, right? So there are many, many, many different properties you want to know about an aluminium alloy. And on the right-hand side, you see, for example, the number of instances. This was, of course, only for the ground truth, so it's a very small thing. Later on, we had much more instances. But you can see that this is it's a very comprehensive list, and that's where this big data back comes in, right? I mean, how do you keep track with all of these properties? How does the brain, it's impossible anymore to have somebody that just learns all of these things and tries to make correlations between all of these properties. Because you could say, well, if my elongation is that big, then maybe my exfoliation will always be, of that value. That there are correlations there that you can draw. And a machine like Watson or what we are developing can essentially do this. So these are all the doping elements, some other property specifications. Okay, so I will not go through these slides because in principle, we should be able to go to the system. Okay, so what am I describing here? So this is, hopefully it's still working. This is a demo that we developed where we can show, this is actually the demo we developed for this metallurgy use case. And here, for example, there are two ways of representing the extracted data. Remember, the methods that you use in cognitive computing, they split up in two things. The statistics part, where you just basically look at what you've extracted, and then the predictive part, in which you try to see or whether you can find trends in the data, right? And predict, for example, in this case, new aluminium alloys. So for example, in the terms of aluminium, so this is the percentage, right? So I think we found something like 100,000 different aluminium alloys from around 10,000 patents. So then you see what is the percentage of aluminium that you typically find. And you see there are definitely trends. So there is a spike here, there's a spike here, and these correspond to the series. The aluminium alloys are cut up in 8 series, depending on their main doping element and all the variations. So of course you can go, for example, to zinc, if this works. So zinc, most of them are 0, but you see there is actually a wide range of zinc percentages. We can go to the ultimate tensile strength, for example, here. So this would be all the properties that have been extracted. And so typically, again, you see that there is a wide variation, and there is typical a mean, and so on and so forth. Okay, that's just looking at the data in a one-dimensional fashion. Now you can say, let's do it in a two-dimensional fashion, I think, which is already much more interesting. So now you can, for example, say, let's take zinc and ultimate tensile strength. Okay, so now let's plot the correlation. Again, this is all real time, okay? So basically, we're going to Zurich at a server there, a cloud server there, where we set up the system. And this is, you can now click and play, and all in real time. Again, this is where HPC comes in, okay? So because you want to be able to push a button and get the result now. I don't want to wait 5 minutes to get a coffee. I want it now. And that's something different. That's a thing that a lot of scientific codes, they typically you submit on a queue and then you wait, and then a day after you do something, and then you do some analysis. But that's not what we want anymore. We want it now. Here now, for example, you see you have zinc on the right-hand side. You have on the x-axis. You have on the y-axis. You have ultimate tensile strength. And what you see is, of course, as we saw, there was many zinc with 0% zinc. But you see there are some trends here. Each dot here is a product, an aluminum alloy product that comes from a patent, okay? And each color is the same patent. So for example, this set of patents, right, has been doing something very interesting. Or no, this patent, sorry, this is just the one patent. But what you see here is a trend that if I increase zinc, my ultimate tensile strength goes up, right? So now that is your first indication, now you can go back to the evidence. It's your first indication, that's the patent that I want to read. Because these guys have been doing something very interesting, right? So this is still exploratory, but it becomes already much more interesting, right? There are also patents that have been absolutely doing very poorly. For example, this guy, properties stay exactly the same. Again, something you might want to read, because it means that they've been doing something wrong. And that's equally valuable. Although in our scientific literature right now, this is not valued so much, but we should. Okay, so for example, another thing that you can do is you can say, well, copper. Of course, the ultimate tensile strength you don't control as much as what you put in. So you can do also, for example, to say the following. Now this one, let's see. Okay, so our cloud is sometimes overused. Okay, so now you see zinc versus copper. What does this tell us? This tells us now, again, simple statistics, but it tells us what is the white space. What have people been trying out ad nauseum, and what have people been trying out or not been trying out? For example, here, we don't find anything. You want to make a patent? Well, make something here. Let's see what it is, right? You also have certain trends. So a lot of people have been doing zinc with a little bit of copper, and vice versa, a bit of zinc with a lot of copper. But there's clearly white spaces. There are also very weird cases like this guy, right? What has he been up to? So outliers. So white spaces, outliers, trends. Okay, this is what you can do with statistics, typically. And if you have, and again, if you think about the last part where I said you need to be able to represent the data in an intelligent way, this is, for example, one of these ways. Okay, where you can see, okay, we have this high-dimensional data, right? We have this unstructured. We have many, many, many different attributes, as I can show you here. So, for example, here. I mean, these are all attributes that we have extracted from this stuff. Somehow you need to be able to represent it. If I tell you, well, you can go into the 50-dimensional space and go look for it, okay, sorry, I cannot do that. Okay, so then let's go to the last part, which is the prediction, which is, in my point of view, the true cognitive part. So far, we've been doing data exploration. Now you want to do prediction. So, what can you do with prediction? You can do two types of predictions, or a hybrid of those. You can say the typical scientific way of doing an experiment, right? If I put in so much magnesium, and if I put in so much zinc, what is going to be my strength? Well, there are computer programs that allow you to do that. You can just put in the crystal structure, put in the correct elements, and then run the calculation, run a DFT calculation, see what your strength is, right? So people have been doing this forever, but this typically takes a lot of time, a lot of expertise, and sometimes you just want to find a good starting point. So, but for example, what we can do now is we can also say, well, let's just look at all the data that we have, give us a rough estimate, and we will start with this rough estimate. If we need to go deeper, we can do the DFT. So that's the idea that is happening here. So for example, if you now say again, so let's take zinc, and now let's take zinc between 5 and 10%. Again, something you can't really do with a real simulation. You put a precise number in there. You don't say a range. With statistic, or with these predictive, or with the Bayesian inference, you can put a range in, right? You can say, roughly that. So it's kind of more fuzzy. And fuzzy is sometimes good, sometimes bad, but I think it's quite nice. So once you say, okay, I have all of this data, now I put a constraint on the data. I basically say the constraint is that zinc has to be between 5 and 10%. And we can play with this, right? Then you can say, okay, so all of this data gives you a mean, an error, a best, and a worst. But obviously, that's a bit restrictive. So you can go you can do a deep dive. We can now go to the ultimate tensile strength. And we see this. This is a correlation plot. So for all the values of ultimate tensile strength, going between typically -1 and 1. But there is no -1 here. -1 means if you put zinc between 5 and 10%, there is no way you will find an ultimate tensile strength of that value. 1 means if you take that constraint, this is a very likely value you will get, right? And now what you see is you have actually multiple peaks. And again, this is what you would expect, because essentially what you're saying is, I have all of my data, I put a fuzzy constraint on it, now give me what are the possible solutions I would expect. Okay? And these possible solutions, there are obviously going to be multiple ones. It would be inconceivable that with just one constraint over all of this 50-dimensional space with all of the different doping elements you can put in, that you would get just one solution. But you get multiple solutions, right? And now you can start going iteratively through that. Now you can say, well, okay, so I like, for example, that, but now let me look at, I like that I have this peak, but actually what I really would like to look at is this. So now let's go there and say, well, let's take, now that I have an ultimate UT, ultimate tensile strength, yeah, exactly this guy. Let's put between 90 and 100, right? So now we do this, we say 90 and 100. So now let's add a constraint, right? And redo the calculation. You like that region? Of course, if you put the constraint in, then you will get the same constraint out. That's what you would expect. But now you can say, well, if I have this zinc, and if I have this UTS, this constraint, now can I ask, how much copper should I put in order to satisfy these constraints? These two constraints, only these two constraints. Well, the system says, well, there's this guy, a big one, and then there is an outlier here. Right? This could be an interesting case to look at. He also found maybe some trends here, and he found a very thing here. And if you remember a bit the graph of zinc versus copper, there was a huge section here where there was with a lot of zinc and a little bit of copper. That's what you get out, right? And again, you can start iteratively going through this data. So what this tool allows you to do is to go through this high-dimensional space, start putting in constraints, and give a fuzzy prediction, a rough prediction of what you would expect given the data. And then once you have done that, then you can say, okay, now, for example, I go through all my data, I put in these constraints, right? Find me maybe a data element that satisfies this or doesn't satisfy, right? Stuff like that. So you can find the evidence again. But sometimes you don't find any data elements, and the reason is that very simple is there is a trend, the system has found this trend, but there is no data element that supports within your constraints, this trend. So then once you're there, then you can say, okay, I found something new. Let's test it out. I can maybe write a patent, right? So this is how the prediction capability works. Now, in terms of the biomedical, I think it's pretty obvious, how you can extend that, right? Now you can say instead of doping elements, you would, for example, have dosages of certain drugs, or you would look at, what we are looking now in the lab is, for example, genes that are connected with diseases and so on and so forth. So there's many, many ways how you can reuse exactly the same type of technology into a completely different domain, right? And again, that's where IBM comes back in. So just saying, okay, transforming business or whatever current practice enabled by technology. This is the technology that we're trying to do. I just want to show you a few other knowledge graphs. So you've seen we've moved on. So this was last summer, right? The metallurgy stuff. Okay, I still have 20 minutes. So, for example, this is now what we're working on the geology. So, if you remember, we had this paper with for geology where you have all kinds of different things. So, and again, so geology is much more messy than metallurgy. So, you have all kinds of rocks. You have geological time ages. You have locations. So, you need to have basically all locations of the planet because they will talk about a certain location. You will have your petroleum wells, you will have your fields, your reservoirs, your basins, you name it. You will have authors that claim all kinds of different things. And this is what we're basically showing here, right? So at this point, we have ingested around 2,700 articles. This will grow. It's still a test case at this point. We have, for example, all kind of geographic regions. Right, so they will talk about, in the Appalachians, we found the rock, the northern Appalachians, we found the rock, and we find that there is some kind of similarity with this rock somewhere in Iran, or I don't know what. Maybe there is a connection there, right? Same age, same type of rock, maybe the geological process was the same, so maybe we can look for, I don't know, carbon. I'm making this stuff up, so don't draw any conclusions from this. But that's basically the process. The way people are thinking about this stuff, right? And so here, we have the petroleum fields, we have the countries, we have the marine regions, and so we have regions. We have authors. So authors is, for example, a very big part because a lot of conflicting theories. And so, for example, now let me go through a typical thing. So you would look at Syria, right? So then, again, on the push of the button, you get all the articles that, for example, mention Syria, but you get also the country Syria or the Syrian desert. You can, for example, click on this, and now you say, okay, so what basins are in Syria, right? Because a basin is basically where people start from to start, for example, drilling for oil. Okay, and then you can say, okay, so which basins are in Syria? There are these basins. Which kind of petroleum fields do we find in here? These ones. For example, now we see that there is, for example, in this basin, we find 2 fields here. Maybe we can go to the west part and see maybe there is also some oil there. So this is the way people start thinking about this stuff, right? They try to find correlations. They try to go through the literature, and they want to see what is in there, right? And this is, again, so this is the way you have to think about this guy here, is essentially more of the exploration phase, okay? It's a bit slow, it seems. Let me show you another one we did. So this is for intellectual property. There, of course, you could say, so this is where we're developing this. So, for example, you have now a new idea. 5 minutes. Good, no, I'm finished, so don't worry. For example, you have a new idea, and now you want to say, okay, so this new idea, is there anything out there already in the patents? Is there maybe another company that is interested in these patents? So this is the knowledge graph we have now. I think for the biomedical, this is now we're looking at the PubMed extracts, the authors. We have now the mesh terms, so this is towards the biomedical. Of course, now we will put in all the proteins, we will put in all the genes, we will put in all the drugs that we have from the drug bank. And then start playing around again with, first of all, in the first phase, just exploratory, and then in the second phase, we will start doing the analytics. And you know what? It's 5 minutes. Do you guys have any questions? Anyway, I think it's coffee now, right? Or is it? Okay. So you can approach me over coffee. But if you have any questions, let me know. Okay? So. Yeah.
But you still have to have the idea of what you are trying to find, because it will not help you to, you have the you need a deep knowledge of what is the subject, and you have to ask for questions you previously have. It will help you to find the answers,
Yes.
but it will not lead you to have the good questions. For example, in genes, or you have to have an idea this gene, and the gene correlates with this protein and this disease.
Yes. So,
But you have that, and you can check if the data supports your idea, but it will not help you to have the idea of the question.
it will in a future I mean, I will say in a year or so. So what this does is now this is a human interface. Okay, that's basically what you're saying. You still need to put in the data. Okay. But these type of queries, once you now again go back to what programming does. If you say now, let's run over all diseases with all genes, and let's start doing queries, random queries, right? Then you can basically write either a huge for loop. Typically, you use a bit of your brain, right? I mean, I'm not going to say that this thing is going to take away, because let's be face it, this is going to help you. It's not going to replace you, right? If you're saying the tool is going to do everything for you, you're out, right? I mean,
So
that's not what we want. We want the experts. The human brain is really good at certain things. What we want to do is accelerate research, right? And I hope I can convince you that this will accelerate your research, right? That you don't have to do all of this stuff anymore. And the second thing is, again, so this is we click now, okay? And clicking again is a human process, right? Think about it again. Now we can say, well, I don't want to click. I want to take a full range of certain possibilities, maybe 2-dimensional, 3-dimensional, I don't care, and now do all the queries, and now I will do statistics on all of these queries and see whether they find something interesting. Then you go towards what you're saying, right? But again, it's a human brain that will say, okay, this is interesting. And don't forget, you can only get out what you put in as data, okay? So sometimes this thing will predict wrong stuff. Simply either the data is not there, the data was wrong, and so on and so forth. So you need a human brain that at the end of the day says, let's correct that, you know? For example, what you could do is you can connect this with a simulation tool and now automatically run. So you do a prediction, a fuzzy prediction that's very quick, and then you verify that with simulations. And in the beginning, your simulations will tell you your prediction was wrong, right? Because you don't have enough data. But then that data gets fed back into the knowledge graph. Now you have a bigger data set, which you do again predictions. And so once you do this iterative, process, you might get a better and better feeling as to, you will just get better predictions. That's just the nature of statistics. The more points you have, the more data points you have, the better your statistics. And so this, I think, goes into that direction. So in the beginning, yes, this is exploratory. I think with the prediction, I think we can already go further. So you can have a hunch, and now you can start playing around. The third phase is we now automatize the queries, and we are working now on architectures, essentially, that will require much less energy. So these things, for example, they run on a power 8 plus GPUs. GPUs require a lot of energy. But if you're doing always the same operation, you can use, for example, FPGAs for that. Then you reduce your energy footprint, and you can do more of them. But then it doesn't have to go. So GPUs are perfect because they go very quick. So you can get your results on the push of the button. If you say, I want to do millions of queries, this you cannot do on a push of the button. It's not possible. But what you can do is you can put that on a cloud system or a thing, let it run overnight. If the energy is not too much, that energy is equal to cost, for people that don't know this. If the energy is not too much or the cost is not too much, you can let it run overnight, then you do your analysis. Or you feed that back into your knowledge graph, and you feed it back into the system. And then maybe your predictions become better. Does that go into you? Good.
Well, in order to make predictions, you are using a lot of data, but you have to create a model to analyze this data. How can you do that in real time? Because well, you can make some clustering algorithms that will work in time, but if you want to get more information about this data, that's very limited. How do you manage to perform well with this data?
So when I talk about models, I'm going back to the physics, chemistry, biology. Those are the models. We go back all the way to Schrödinger's equation if it has to be. Okay, so there is a certain part, so you don't have to just think models in terms of, you know, the typical big data models or that people are thinking about. When I'm talking about models, I'm talking about, you know, what you learn in school, right? Your background. I'm talking about the fact that, I don't know, whatever. If you can go back to silicon and see if you dope it, then maybe, you know, the band gap changes and stuff like that. These are all, I mean, it's a wealth of information that's in there, right? And I'm not going to say I'm going to throw that all out of the window and just base this on my data. I will use whatever I've learned in all of these textbooks, which has an incredible value. These are my models, and my data is now going to enrich these models. Because typically, whenever you have these models and you say, but you know, if only I knew that coefficient, you know, then I could do it. Fine. But what if you have an estimate of this coefficient? Well, then you can start doing this prediction there, right? So that's, I get your point, and that's a very important one and that is part of it. And then so in terms of decisions, when you do a support decision, you have to do this. But what I'm talking about with models is really back to basics, back to, you know, what have you learned? That's also where this goes back to you. You need to have an expert. You know, you cannot do metallurgy without knowing what aluminium is, right? It's not possible. I mean, in my view, it's not possible, but maybe in the future it will be. But if I don't know what copper and aluminium and zinc is, to find a new aluminium alloy is going to be very, very hard. So, for example, one of the funny things that we encountered was the machine, for example. When we were doing the parsing, it didn't know the difference between volt and vanadium. Now, vanadium is a doping element. Volt is, you know, electricity, is a unit of electricity. Of Spannung, I would say. I don't know. But you have to teach the system that vanadium and volt is not the same thing. And if it makes a link there, well, it's going to be completely wrong. So there, again, you need an expert that goes back to basics. Says, okay, volt has to do with electricity. Vanadium is an elementary atom, right? So we are working. I mean, we are working with many experts in the field. When we are developing these things, it's not that we are somewhere in the office and just, I will just do it myself. For the IP, for example, we work with the lawyers, obviously. For the metallurgy, we work with the best in the business. For medicine, we work with people in our lab and also now with some other companies. For material science, material science, I am a material scientist and I also have a lot of people that do chemistry and so I know the stuff, okay? And I know also some people, some PhD students of mine that really know the stuff. So I don't need to ask anybody, I can ask myself. But again, so you need to have that basic knowledge. And it's not enough anymore to just be a computer scientist and say, well, I don't need to know anything about physics or chemistry or biology. Or geology. For this geology, I need to go read geology books. You know, I don't know what the Miocene is. The Miocene is now a geological age. I know this now, okay? But I mean, you need to put it in, right? So this is where it all comes together. That's also what it makes it super interesting. I mean, you're not doing, I mean, when you're, at least in our group with Cognitive Foundations, you will learn different fields of research, and you will have to. And if you don't, okay, so you need to have that will of learning. That's also what I'm looking for in people, okay? I have computer scientists, but in the group, and we will force them to learn physics, and we will force them to learn other stuff, and if they don't want to, you need to. Okay, I hope that inspires you to do it, okay? Because I don't want to scare you here. It's really cool stuff, okay? You will learn stuff you have never thought about, you know, and this is the cool part, okay? And I hope I can convince at least one or two of you guys to start working with us. And otherwise, I will have failed, I guess. So it's like that.